Hi everybody. Today my topic is eigenvalue and eigenvectors. Let's move ahead to see how we can explain these two things, eigenvalue and eigenvectors. Here I have taken a matrix, it is 2 by 2 matrix, and this is a U vector. Now if I multiply these two, result is 4, 2, and we can write this like this, 2, and this vector is 2, 1. So what you can see here, this U vector is repeated. This is the most important point to notice these points, that if a vector after multiplication with a matrix repeated, I mean it comes back again with a multiplication with a scalar value, then this vector itself we call eigenvector, and this scalar value it is eigenvalue. This is vector, this is value. So these two are the eigenvalue, and U is the eigenvector. Now if we look at this image in the graph, what you can see, 2 times of U vector. So here first this was U vector, I drawn 2, 1 because it was 2, 1 coordinates. So this is the U vector. After multiplication 2U, so it comes like this, 2U double. So what I can say, A stresses or dilates U. That's what we have seen here. Now if we take another matrix and another vector and multiply these two, we get 4 and this repeating this U vector, 4 multiple of repeating this U vector, so 4U. So image, it shows this U 1 by 1, then it is 4 times stressed, 4U. So this 4, it is eigenvalue, this U vector, it is eigenvector. So this is eigenvalue and this U is eigenvector. Now in the next slide we'll see which is not eigenvector. Let's go to the second slide. Here I have taken a vector like before, and there is a this is actually matrix. I have taken a matrix and this is the vector. So if I multiply these two, what is the results? This. What image says? 1 minus 1, 1. So this is the vector. After multiplication, it reaches here, not in the same line. So as well it is not repeated. There is no multiplication scalar value. So not an eigenvector of A. And image also says like that. As well here I have taken again another matrix multiplied with a vector u. We got 3 2. This is the image u 1 0. So this is the vector. After multiplication 3 2, 3 and 2, so it gone here. So it is not stressed in the same path. So of course it is not an eigenvector of A. So now it's clear for us which one is eigenvector, which is not eigenvector. Now here I have taken a square matrix, n by n matrix. In generalized form, I can write Aij. Assume the vector equation as Ax equal to lambda x. This is matrix multiplied by vector equal to, this is eigenvalue and this is eigenvector. What we have seen in the first slide, accordingly this vector equation is written. So x is an unknown vector, lambda is an unknown scalar, but we know it is lambda is eigenvalue and x is eigenvector. So we seek values of lambda so that system has non-trivial solution. So what we will do? So we'll do something here from these equations. Ax minus lambda x. So surely we can write a minus lambda in bracket x equal to 0. But is it correct? That's what I have written like that. Is it correct? No, it is not correct. The reason a minus lambda is not defined because A is a matrix, lambda is a constant. We cannot subtract like this. So we have to do what is the solution for this? We have to write lambda x as lambda ix, identity matrix. Its value is 1. So previous slide we had ax equal to lambda x. Only additional things we put one identity matrix here. Why? Because if we bring it on the left side and now if we take x out, putting a minus lambda I inside the bracket, now this is logical because this is matrix, this is also lambda is multiplied with a matrix. Now it is not is constant, so it is in a sense that this is also matrix, this is also matrix. Now we can write it in subtract form. That is why I wrote here A minus lambda I. Now it is defined. And A and lambda I square matrix of the same size. As we know, Ax equal to 0. To have non-trivial solution, it is needed that determinant of A equal to 0. In my previous video on trivial solution and non-trivial solution, regarding this I discussed in details. If you have interest, you can go through that video. So here I repeat again, Ax equal to 0 to have a non-trivial solution, then it is needed also that determinant A must be equal to 0. So here our equation is A minus lambda I into x equal to 0. So for this case, this A determinant we have to find. So here also we wrote this full area, I mean full part, A minus lambda I determinant we need to find. It will be equal to 0. Now values of lambda that cause the system Ax equal to lambda x to have non-trivial solution are called eigenvalues. Already regarding eigenvalue I discussed in slide 1 and 2, but here in a statement form it is repeated that to have non-trivial solution we need the value of lambda. That is the most important point. We need the value of lambda, because this lambda it causes the system Ax equal to lambda x to have a non-trivial solutions. And it is eigenvalue. And we call it again as a eigenvalue of A. So for each eigenvalue, actually these all statement it will be needed when we will go in the next slides. So I am putting all the statement here. If we understand this, so it will be easy for us to solve the problem which comes in the next slide. So here I have written for each eigenvalue there is a non-trivial solution of the system, and this solution is called eigenvector. Already we got the idea about eigenvalue and eigenvectors. So here I am taking two equations, 4x plus y equal to lambda x. So wherever we see lambda, right away we understand that this lambda means it is eigenvalue. So from these two equations, we can write like this, because coefficient of the variables we take in a matrix form and xy are the vectors, lambda again xy vectors. This is repeated. Now This matrix, suppose it is A, this is X, this is lambda, this is X. So what we get? So we got A, X, lambda, X. So it is like Ax equal to lambda X. To have non-trivial solution, already in the previous slide we discussed, we need this determinant equal to 0. So what we will do? A matrix, we know this. That's why I wrote all the name of this. So A is this one right here. Lambda is this, right? Lambda. I, we know, diagonally all will be 1. So, and this will be 2 by 2 matrix. This is also 2 by 2 matrix. Already we discussed before. So we can write like this. So this minus this, only lambda will come inside by multiplication. Lambda, lambda. Now if we subtract this from, subtract this minus this, then we get like 4 minus lambda, 3, then 1 minus 0 means 1, 2 minus lambda, so it comes like this. Now it's easy, we can multiply, cross multiply. So we get like that. So this will be 4 minus lambda multiplied by 2 minus lambda minus of 3. So this is our simplification form. This is quadratic type. So when we will put the value 0, this equal to 0, we will get the value of the lambda. So last equations I brought it here again because not to forget what it was. Now this equal to 0, so it means this equal to 0. We can solve lambda equal to 1, lambda equal to 5. Now using these lambda values, we will find non-trivial solution. That's what we just discussed in previous slides. So what we will do, we will take eigenvalue lambda equal to 1. First we will take this one. If lambda equal to 1, then system equation becomes as this. Because this equation we had before, because this is A, this is minus identity matrix, and there was lambda here, but that lambda is 1. So it is 1 here, but we can't see anything. And this is the vector, and this is the right hand side 0 vectors. So doing this subtractions, we find this. Now from this equation we can write two equations very easily. This one we can write two equations. 3x plus y equal to 0, again 3x plus y equal to 0. Now from this equation we find y equal to minus 3x. So looking at this equation, we understand there are infinite number of solutions, because if you put x equal to 1, you get y equal to minus 3. If you put x equal to minus 4, you get y equal to 12. And so on. It means lot of solutions we will get. That is why it is written infinite number of solution. Now x equal to t, if we assume that x equal to t, because as we are finding whatever value we are putting for the x, in turn we are getting the value of y. So in generalized form we are writing that if we assume x equal to t, then y equal to will be minus 3t. Now eigenvector corresponding to lambda equal to 1 is this x vector, it will be xy, we know that, and it will be like x, we already assumed it is t, so this is t, and if x is t, then y is coming minus 3t, so we have to write here minus 3t. Now if we take out t, so inside we are getting 1 minus 3, this vector. So what we are getting? So corresponding to lambda equal to 1, there is infinity of solutions. You know what, lot of values you can put and we will get the value. Putting t equal to 1, 2, 3, whatever you want. So there is infinity of solutions. Now before we used lambda equal to 1. Now we have remaining lambda equal to 5. Then system unit, this system equation becomes, we know this is the equations, so we need the solution of this. So what we will do, A, we know the A matrix, minus, before we remember that we put lambda equal to 1. Now we are putting lambda place, we are putting 5, and this is identity matrix, x vector and 0, 0, 0 vectors. So what we are getting? So 4 minus 1, 4 minus actually 5, so it will be minus 1. This way we get this matrix, then this x vector, then equal to 0, 0. So what is happening? We are getting two equations. Minus x plus y equal to 0. Another is 3x minus 3y equal to 0. So these are the equations. Y equal to x, because minus x plus y equal to 0. So we can write very easily y equal to x. Now if x equal to 1, y will be 1. If x equal to minus 4, y will be minus 4. And so on. It means so many solutions we will get. Now we want to write it in generalized form. So x equal to minus t. Then y equal to will be t. So eigenvector corresponding to lambda equal to 5 will be x equal to xy, we know this x vector, I mean, now x value is t, y value t, so we are writing t and t. Now t taking out, inside 1 1, this is the eigenvector. So corresponding to lambda equal to 5, there is infinity of solution, because is t value, it can be 1 2 3 4, whatever value you put, you will get solution. So lot of solution is there. So there is infinity of solutions. And that's for all for today. Thanks for watching.